Hey everyone, and welcome back to the channel. Today, we're diving deep into the world of cloud computing and DevOps. We're going to demystify some of the biggest buzzwords you hear all the time: virtual machines, containers, cloud scaling, terraform, ansible, and kubernetes. By the end of this video, you'll have a solid understanding of what these technologies are, how they work together, and why they're so crucial for modern software development. So, grab a coffee, and let's get started. First up, let's talk about a classic debate: virtual machines versus containers. When should you use one over the other? Imagine you want to build several different houses on a single plot of land. One way to do this is to give each house its own complete foundation, its own plumbing, its own electrical system, everything it needs to be totally independent. This is like a virtual machine, or VM. A VM is a complete emulation of a computer system. It has its own operating system, CPU, memory, and storage, all virtualized on top of a physical server. This makes virtual machines incredibly isolated and secure. If one VM crashes or gets a virus, the others are completely unaffected. This is why you'll see virtual machines used for running legacy applications that need a specific old operating system, or when you need strict security boundaries between different applications, like in a multi-tenant environment where different customers share the same hardware. The downside? They're heavy. Each VM carries the full weight of its own operating system, which can be several gigabytes. This means they're slower to start up and use more resources. Now, let's go back to our land analogy. What if instead of building separate houses with separate foundations, you built one large apartment building? All the apartments share the same foundation, the same main plumbing, and the same electrical system. But each apartment is its own self-contained living space. This is a container. A container is a lightweight, standalone, executable package of software that includes everything it needs to run: code, runtime, system tools, system libraries, and settings. The key difference is that containers share the host server's operating system kernel. They don't need to boot up a whole new OS. This makes them incredibly lightweight, fast, and portable. You can spin up a container in seconds, compared to minutes for a VM. This efficiency is why containers, with Docker being the most famous technology here, have become the standard for developing and deploying modern microservices. If you have an application broken down into many small, independent services, containers are your best friend. They allow you to package each service individually and run them anywhere consistently on your laptop, on a test server, or in the cloud. So, to recap, need strong isolation and a full OS for a legacy app? Think VM, need to run modern, lightweight, portable microservices quickly? Think containers. In many real-world scenarios, you'll even see them used together, containers running inside of virtual machines to get the best of both worlds: the portability of containers and the security of virtual machines. This brings us to our next topic: how the cloud scales. The whole promise of the cloud is elasticity, the ability to get computing resources when you need them and release them when you don't. This is what we mean by scaling. There are two main ways this happens: vertical scaling and horizontal scaling. Let's use another analogy. Imagine you have a single delivery truck. Vertical scaling is like upgrading that truck. Your business is growing, so you replace your small truck with a bigger, more powerful one that can carry more packages and drive faster. In cloud terms, this means adding more resources to a single server. You increase its CPU, add more RAM, or get faster storage. This is simple and can be effective for a while. especially for applications that can't be easily distributed, like many traditional databases. But there's a limit. Eventually, you can't just buy a bigger truck. They don't make them that big. And if that one supertruck breaks down, your entire delivery business stops. That's where horizontal scaling comes in. Instead of buying a bigger truck, you buy more trucks of the same size. If one truck breaks down, the others can still make deliveries. As business grows, you just keep adding more trucks to your fleet. In the cloud, this means adding more servers to your application. Instead of one massive server, you run your application across 10, 100, or even thousands of smaller, identical servers. This is how giants like Google, Netflix, and Amazon handle their massive traffic. This approach is more resilient and, in theory, infinitely scalable. If one server fails, a load balancer simply redirects traffic to the healthy ones. When traffic spikes, an auto-scaling system automatically adds more servers. When traffic dies down, it removes them, so you're only paying for what you use. This is the true power of the cloud. Most modern cloud-native applications are designed for horizontal scaling, often using containers to make it easy to replicate the application across many servers. So, we have our applications neatly packaged in containers, and we have a cloud that can scale on demand. But how do we manage all this infrastructure? Setting up hundreds of servers, networks, and databases manually is a nightmare. It's slow, error-prone, and impossible to replicate consistently. This is where infrastructure as code, or IAC, comes in. And the king of IAC is Terraform. Terraform, created by HashiCorp, allows you to define your cloud infrastructure, your virtual machines, your networks, your storage, everything in human-readable configuration files. It's like having a blueprint for your entire cloud setup. You write code that says, I need 10 servers of this type, a database with these specs, and a network configured like this. Then, you run the Terraform apply command, and Terraform talks to your cloud provider, whether it's AWS, Azure, or Google Cloud, and builds everything for you, exactly as you described. The beauty of this is that your infrastructure is now version-controlled, repeatable, and automated. Need to create a new testing environment? Just run the same Terraform code? Need to update a server? Change one line of code and apply it? Terraform makes managing complex infrastructure predictable and scalable. It's the foundation for modern cloud operations. Now, Terraform is fantastic at provisioning the infrastructure, the servers, networks, and so on. But what about configuring what's on those servers? Installing software, managing configuration files, starting services. That's where a tool like Ansible comes in. Ansible is a configuration management tool. If Terraform builds the house, Ansible furnishes it. Ansible uses simple files, written in a format called YAML, to describe the desired state of your servers. You might write a playbook, as it's called, that says, ensure the web server software is installed, make sure this configuration file is in place, and ensure the web service is running. Ansible then connects to your servers, typically over a standard connection like SSH, and makes it so. It checks the current state and only makes the changes needed to reach your desired state. Unlike some other tools, Ansible is agentless, meaning you don't need to install any special software on your servers beforehand, which makes it very easy to get started with. You can use it to configure a handful of servers, or thousands. So, you use Terraform to create the servers, and then you use Ansible to configure them perfectly, every single time. This combination creates a powerful, fully automated pipeline for your infrastructure. Finally, we arrive at the conductor of our container orchestra, Kubernetes. We talked about how great containers are for running microservices. But imagine you have an application with 50 different microservices. You might need multiple copies of each one for reliability and scale. Suddenly, you're managing hundreds, or even thousands, of containers. How do you deploy them? How do you make sure they can talk to each other? What happens if a container crashes? How do you scale them up and down based on traffic? Managing this manually is impossible. This is the problem Kubernetes solves. Kubernetes, often abbreviated as K8s, is a container orchestration platform. Think of it as the operating system for your entire cluster of servers. You tell Kubernetes, I want to run 5 copies of my web server container and 3 copies of my database container. Kubernetes then takes over. It finds the best servers to run those containers on. It handles networking between them. If a container or even an entire server fails, Kubernetes automatically restarts the container or moves it to a healthy server to maintain your desired state. It can automatically scale the number of containers up or down based on CPU usage or other metrics. It handles rolling updates to your application with zero downtime. In short, Kubernetes automates the deployment, scaling, and management of containerized applications. It abstracts away the underlying servers, allowing you to focus on your applications, not the infrastructure. While it has a steep learning curve, its power and flexibility have made it the industry standard for running containers at scale. So there you have it. A whirlwind tour of some of the most important concepts in modern cloud computing. We started with the building blocks, using VMs for isolation and containers for portability. We saw how the cloud uses vertical and horizontal scaling to provide on-demand resources. And we learned how we manage it all using powerful automation tools. Terraform to build the infrastructure, Ansible to configure it, and Kubernetes to orchestrate our containerized applications. Each of these tools solves a specific problem, but together they form a powerful ecosystem that enables developers to build and run complex, resilient, and scalable applications in the cloud. I hope this cleared things up for you. If you found this video helpful, please hit that like button and subscribe for more content on cloud and DevOps. Let me know in the comments if there are other topics you'd like me to cover. Thanks for watching, and I'll see you in the next one.